Chapter 2A, Marginal, Conditional, and Joint Probability. Take a minute and read through the why and the learning objectives and the vocabulary. In this activity, we're going to be constructing and analyzing two-way tables and the associated probabilities that we can calculate. Example 1 contains data from students in a statistics class in Los Angeles. So this is what we call a two-way table. If you look at the columns, you see those are all eye color possibilities, and the rows are hair color possibilities. So because there's two variables, eye color and hair color, and they're both contained in the table, we say this is a two-way table. Imagine a three-way table would be 3 dimensions, and a four-way table would be in the fourth dimension, hard to draw. So typically we work with two-dimensional tables in the form of two-way tables. Question A asks us how many students in the class have brown hair and green eyes. So this is to check to make sure we're reading the table correctly. So for brown hair and green eyes, we come to the brown hair color, and then we find the column for green eyes. And so the 2 here overlapping between that row and column tells us 2 students have brown hair and green eyes. Similarly, we can check to make sure we're understanding the table by checking to see how many have black hair and brown eyes. So if we come to black hair and follow it over to the brown eye column, we see that's 7 students. So now if we want to figure out how many students have brown hair, we come to the hair color brown and we total up all the eye color possibilities in this last column. The total is in the last column, the total for the row. So we see we have 10 students with brown hair. Now if we want to make this a probability, we would say the probability of brown hair is 10 out of the 36 total students. As a fraction, we can reduce that down to 5 out of 18, or as a decimal rounded to 4 places, we could say 0.2778. Similarly, we could say how many students in class have brown eyes. So we come up to the brown eye column and we find the column total down here in the last row. And so that's 17. If we want to make it a probability, we say 17 out of 36 students have brown eyes. That's a probability of having brown eyes, 17 out of 36. As a decimal, we could translate that to 0.4722. These are known as marginal probabilities because where are we getting these values from? When we did the probability of brown eyes, we got that 17 out of the margin. So the margins are the totals for the eye colors or the totals for the hair colors. So what do the values in the bottom row represent? Those are the eye color totals. Similarly, the values in the right-hand column are the hair color totals. So these are what we call margins. And we put a note here for any two-way table representing 2 categorical variables, the totals in the bottom row in the right-hand column are the marginal distributions. So if we look back up here and check, we see these total up to 36, all the possible hair color totals, and then all the eye color totals also total 36. So this is a distribution. If we were to make these fractions, 6 out of 36, 7 out of 36, 10 out of 36, and 13 out of 36, they would add up to 36 out of 36 or 1 total. So we say this is a marginal distribution. Here are the values for hair color, and then down here are the values for eye color. What does that value in the bottom right-hand corner represent? Well, that's the total students in class, and you can check the addition. If you tally up all the eye colors, those add up to 36 students total, and if you tally up the hair colors, those also add up to 36 students total. Either way, whether you're adding the eye colors or the hair colors, they should both tally up to the total, so it's a good way to check your two-way table to make sure you haven't made any mistakes, to verify that everything totals the total number of students you're expecting. So now, question H asks us, what fraction of students in the class have brown hair and brown eyes? So this is what's known as a joint probability calculation. So if we look back at the table, we find where does brown hair overlap with brown eyes, and we see there's 5 students. So these students have to have 2 conditions met. They have to both have brown hair and brown eyes. So we call this a joint probability. They have both of these conditions. And so that probability is 5 out of 36. Or is a decimal 0.1389. Question I asks, what fraction of red-haired students in the class have green eyes? So this is known as a conditional probability because we're conditioning on the fact that the students have red hair. As a probability, we write it this way. We say P for probability of green eyes, and then this bar tells us that there's a given condition following that, and in this case, the given condition is red hair. So if we go look at the two-way table, we see there are 7 students total with red hair. This is our denominator because our given condition is that they have red hair. We're not counting all students. And then we see 3 of those 7 students have green eyes. So this is how we come up with our conditional probability, the part out of the total. The denominator for conditional probabilities, since we're restricting the table, is always going to be a value from one of the row totals or one of the column totals. Question J says, what's going to happen if instead of having 36 students, we had 5 students, but we still had the same number of blonde-haired students? So if there are 36 students total and you still have 6 blonde-haired students, the probability of blonde hair would be 6 out of 36, or 0.1667. If we change to a class with 500 students, but still only have 6 blonde-haired students, then the probability of blonde hair is 6 out of 500, and that reduces down to 0.012. So this is a much smaller probability than 6 out of 36. So to show the difference in the class sizes, we need to represent the blonde students as a fraction or proportion, in other words, as a probability. So we don't ever want to just say there are 6 blonde students in class. We want to say there are 6 out of 36 or there are 6 out of 500, because those probabilities are very different. Example 2 looks at a table from a 2010 Pew Research poll. It asked 1,306 Americans, from what you've read and heard, is there solid evidence that the average temperature on Earth has been getting warmer over the past few decades or not? They also asked people for their party and ideology. So we have in the rows the different party and ideology choices, and in the columns the different responses for this survey. So notice these are written as proportions instead of values, and the total here is 1. So anytime we're working with proportions, we want to make sure that the table total is 1. And similarly, you can check all of the row totals add up to 1, and all of the column totals also add up to 1. So our first question is believing that the Earth is warming and being a liberal Democrat mutually exclusive or not. So if we look here, liberal Democrats, we see 0.18 of the total people in the survey, or 18%, are liberal Democrats who believe that the Earth is warming. So this is definitely not a mutually exclusive relationship. There is some overlap. Remember, mutually exclusive means disjoint or no overlap. So we say these are not mutually exclusive since 0.18 of the survey respondents are liberal Democrats who do believe the Earth is warming. Question B asks, what is the probability that a randomly chosen respondent believes the Earth is warming or is a liberal Democrat? So we can add up the 0.60 total who believe the Earth is warming plus the 0.20 row total of the liberal Democrats. But then we need to subtract out this 0.18 because notice that 0.18 got double counted. It got counted in this column total and in the row total. So we don't want to be double counting, so we subtract out the overlap and we get 0.62. You could have also come here and added up all these values and then making sure not to overlap, added up these other values, and you would have gotten the same result. Question C asks, what is the probability that a randomly chosen respondent believes the Earth is warming given he or she is a liberal Democrat? So now our given condition is that the person is a liberal Democrat. So our denominator is 0.20, which corresponds with the total Liberal Democrats in the survey. Remember, when we're doing a conditional probability, our denominator is the total for that condition. In this case, it's the row total for Liberal Democrats. And 0.18 out of that 0.20 believe that the Earth is warming. And so if we divide, we get 0.9. If we wanted to make it a percent, we'd say 90%. So you could say a statement like 90% of Liberal Democrats believe that the Earth is warming. Question D asks, what is the probability that a randomly chosen respondent believes the Earth is warming given he or she is a conservative Republican? So now our given condition is conservative Republican, so that row total, 0.33 of the conservative Republicans in the survey, is our denominator. So we've got 0.11 out of 0.33, that's 1/3, or as a decimal, 0.3333. So you could say 33% of conservative Republicans believe that the Earth is warming. Question E asks us to find what is the probability that a randomly chosen respondent is a moderate liberal Republican given that he or she does not believe that the Earth is warming. So now they've changed the given condition to be that the Earth is not warming. So our denominator is that 0.34 column total of the not warming column. And then our numerator is the 0.06, the part of the survey that were moderate or liberal Republicans. So if we divide, we say this is 0.1765 as a proportion. As a percent, we could say 17.65% of those who believe that the Earth is not warming are moderate or liberal Republicans. So example 3 gives us a complex probability problem. So this is about mandatory drug testing. Some stores have it, so we're going to suppose that Walmart might have it. And so our test attempts to identify users of illegal drugs such as cocaine. Let's assume that the test is 95% accurate. This means that 95% of the time, a positive result will accurately identify a drug user. So that means it's going to be wrong 5% of the time for a positive result. Similarly, 95% of the time, a negative test result will accurately identify a non-drug user. Let's assume that 4% of the employees are drug users. So we want to fill in this table, and we're told to use a hypothetical sample of 10,000 employees. And one reason we choose 10,000 is that's a large enough number to ensure that the calculations are whole numbers, so we're not in messy decimals. So the very first value I filled in the table is a 10,000 because I know that's the total. Now we assumed 4% of the employees are drug users, so I can calculate 0.04 times 10,000 to get 400 drug users. So in the drug user yes column, that's where I enter my 400. So now by process of elimination, I know this has a total 10,000, so I can say 10,000 minus 400 leaves me with 9,600 of the employees who are not drug users. So now to fill in the rest of the table, let's think about the accuracy of the test. We know 95% of the time, a positive test is going to accurately identify a drug user. So that means the drug test is going to come back positive 95% of the time that the person is a drug user. So we multiply 0.95 times 400 because that's our total drug users, and we get 380. Then we know 5% of the time it's going to come back negative incorrectly, so we can check 0.05 times 400 is 20. You could have also said 400 minus 380 and seen the 20 there. Now let's look at how we fill in the drug user no column. So we're working from this base of 9,600 employees who are not drug users, and we know it's going to come back correctly negative 95% of the time. So if we check 0.95 times 9,600, we get 9,120. And then for a positive result, that's a wrong result or an incorrect result, we will calculate 5%, 0.05 times 9,600. Make sure when you're multiplying with percents, you always translate them to decimal first before multiplying. And we get 480. You could have also found this result by saying 9,600, subtract 9,120, and that equals the 480. So then we tally up our rows and our columns. So if we add up the rows, we get 380 plus 480 is 860. and 20, and 9,120 is 9,140, and you can check that these add up to 10,000. Similarly, we know 409,600 will add up to the 10,000. So now we want to figure out, well, what's the probability that the person is not a drug user if they get a positive result? This is what we think of as a false positive. So the two cells we have to use are not a drug user and getting a positive result, the 480 people here, out of the total who got a positive test, the 860. This is a conditional probability, and we're conditioning on the fact that the drug test came back positive. So we see 480 out of 860 is 0.5581 probability. So this is more than half. So these are more than half of the positive test results are not going to actually be drug users because you have so many people in the employee pool and very few of them are drug users. So it's very important to check tests like this multiple times for false positive results, and which is what they do in medical testing.